Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So, today we're going to be talking about priority queues. Now, just to give you a flavor for a priority queue, you may have heard of what a queue is previous to this class, or you may have even seen priority queues before. So, if you're not familiar with a priority queue, you could think of it in a couple of different ways. There's a couple of ways you can view a priority queue at least. So, one, you can view it like a queue, as in, like, imagine you have a line, and you have all your lovely friends getting in line to get their favorite drink. And there's a front to the line, and so you have all your friends, they sit in this line, they're waiting. They wait in the line, and they're all just waiting in line. But the friends all enter from the rear of the line, and whenever our lovely friend gets served their favorite drink, they leave the line, right? They're done. So you may know of these as NQ, to enter a line, and DQ, to leave a line, or enter or leave the queue. So one way you can view a priority queue is that, imagine instead of it just being where it's first come, first serve effectively, or first in, first out, instead it's built on top of this. Imagine you had a system where you had people that are very, very important that can come into line. Say, a good example of this actually would be, if you've ever heard of it, is in a hospital, like for example, triage. So they do an initial assessment of how desperate is it for you to get taken care of first, right? So in a setting like this, say for example, you enter the hospital and you say, I don't know, say you're like me and you just accidentally fall and trip and you get a sprain on your wrist. It may not actually need to be really taken a look at for quite a while, right? However, if somebody came along, say I came in the door one day and I don't know, maybe I fell and I don't know, my leg just went like this. I might need to get seen earlier, possibly, or even it could be even more severe. So if there's a more severe issue that needs to get taken care of, they may be placed closer to the front of the line so they get served earlier, right? So this introduces the idea of a priority. So you might ask, okay, so how does this change everything from that perspective? Well, if I just simply am dequeuing, or what I'm going to refer to as a removeMin operation, it'll remove whomever or what element is sitting at the front of the queue, and that will always have the highest priority. Now, in the definition I'm going to give you, highest priority means it has the smallest key. So keep in mind that you can always define a priority queue where it's the largest value for the key, but I must stress that it's really analogous stuff. We'll see this. So this is one way you can look at it. Here's another way you can look at a priority queue. So I must stress that, remember, each one of these elements, I'm going to introduce the idea of a priority. So each element that I'm going to put into this priority queue has a key or priority, and it has value or data. So this would be the equivalent of, say, your data. Say if you're imagining like a linked list, for example, you have a data attribute. This would be what I'm referring to. But you have a key or priority, just like if I'm in my hospital triage situation, I want to be able to tell you, yeah, this is more severe, this is less severe. I need to see these people first if they're more severe, for example. Or say, I don't know, another good example is that if you're in a line, for example, if you ever go to some government buildings, for example, or some offices, they'll have it where if they see you the first time, they give you a little sticker, or they give you a special little token that you can enter the line much earlier on rather than having to wait. This is another example of how a priority queue could sporadically appear in such a system. So queuing is this very interesting and broad concept. Priority queues is just a generalization of this. So here's another way you can think about a priority queue. So you can also just think of it like a bucket. Just think of it like a bucket. And here's the idea. So imagine my most important priorities are this red thingamajig. The ones that are least important are my blue thingamajigs. And then, let's say, after the blue ones, the next, so let me just order these. So this is least important. This is the next of the least important. This is a little bit more important, and this is the most important. So what I can do is I could just view all these people in my line. Instead of viewing it like I'm organizing them, I could just throw them all in my bucket here. So what happens is I can always insert an element into the priority queue. So for example, I can insert this one here. And now I have a whole bunch of elements in my priority queue. Now, if I wanted to do what we're going to refer to as a removeMin operation, this will remove and return the element with the minimum key. Now, I told you that each one of these has a different priority. If I wanted to do a removeMin operation out of my bucket, which one should I take out? Which was the most important one? The one that sticks out the easiest for you, right? It's the red one, right? So I would take this one out because it has the highest priority. So keep in mind, highest priority means smallest value in our representation here. So it's a little bit weird at first, but I can assure you, you can always define it so that they're both the exact same idea. Both highest means highest key. But yeah, so if I did a removeMin operation, I would remove the red one. It's gone. It's gone. And then if I did another removeMin operation, I would get one of these yellow ones. It's gone. It's gone. Don't, by the way, if that represents something rather important, just don't throw them away like that. This is just more for dramatic purposes. So anyways, you can keep doing this, right? I can take out the yellow one. This is another one. I can removeMin another one. Yes. So wonderful question. Now, the thing about the priority queue is that all we care about is the value of the priority. So we're not really going to be considerate of if, say, for example, one of these, say, hypothetically speaking, one of those yellow ones came in earlier on, and then another one yellow that was yellow came along. For our ADT, we won't make any distinction between the two. So whichever one is the yellow one, I could take any one of the yellow ones. That's a wonderful question. So this is why one thing about this representation might throw you off is like, okay, well, what if this person was there before you? So who cuts in line, right? Like, do they come before you or come after you? In our representation, it doesn't matter. That's what I'm basically saying. But yeah, no. Does that answer your question? Well, keep in mind, it depends on the underlying data structure. So depending on how we want to represent this data, that's how we'll select out which one comes out, if they have equal priority. So that's how it's going to ultimately play out. Now, I'll tell you, if this matter of ordering really matters, what we can always do is either we can enforce this in the underlying data structure. So when we implement the data structure, we can say, okay, if they have equal priority, I only put it in the first spot that it should go, as opposed to going all the way to the frontmost part of, say, my line, if they have equal priority. So it shoves them as far back, but with the same grouping of people with the same priority, or same elements with the same priority. Or another way is you can always enforce it so that priorities actually do measure something a bit more beyond just, so for example, if, say, for example, there's two individuals, say my triage situation, that have equal priority. Now, when I made that assessment about their priority, I assumed that they're both of equal importance. So it wouldn't matter which one I pick, at least from this kind of abstract view of a priority queue. But yeah, so there are ways you can enforce this kind of behavior, which if you want like the earliest one to come out first, or the later one to come out first. In our description of a priority queue, it doesn't matter. It doesn't matter. Whichever one has the so-called minimum or minimal key, that's the one you take out. So there can be many with the same priority, but just as long as you take out one, that's okay. No, you're welcome. No, wonderful question. I like these kind of questions. So anyways, so the big thing is that these keys or priorities, they're comparable. So they could just be numbers, for example. And here are the main operations. You have insert. You just simply insert the element. So you create an element. The pair is just a key and a value. and you put that into the priority queue. Notice I'm not saying anything about how you do this. Remember, this is just an ADT, right? I'm telling you what it is, I'm not telling you how it's done. Then I have the min operation. This is quite analogous to your front operation in a queue, for example, the one that lets you take a peek at the front of the queue. This is just the equivalent of that, except I just get one with the minimum key. And null if the priority queue is empty. If it's empty, it's quite self-explanatory, right? If the priority queue is empty, then you return true, meaning it has no elements. Otherwise, you return false. Size tells me how many elements are in the priority queue, and I already told you about removeMin. But yeah, these are the operations that we're going to be responsible for our priority queue. Now, I must stress that you can always define more operations, like with any other ADT. These are just standard ones that you'd run into for our priority queue. So are there any questions before I proceed? So does everybody understand the idea of a priority queue? So it's just a queue where all we've done is enforced priorities on the elements, and the ones with the higher priorities, they go to the front of the line, as opposed to the ones that have lowest priority that stay towards the back of the line. But yeah, so there's many applications for priority queues. So I mentioned about modeling, for example, triage situations. So if you're running simulations for triage, for example, or even are actually modeling a system that it has a queuing system, triage is very naturally one that matches up with a priority queue. And you can always encode more information if you need to, for example, take care of those tie breaks, for example. But yeah, no. Another one, of course, just because it is a type of queue, it's a much more broader class of queues. You can always model this in many other settings. For example, some scheduling algorithms use priority queues. Some graphics applications use priority queues. For example, if you're really big into graphics, there's a nice classic algorithm that's called Painter's algorithm. It's used for drawing, for example, three-dimensional. So if you have all your polygon information for what needs to be drawn to a screen, the order in which you draw them typically goes from back to front. What you do is you assign the depths of whatever you're trying to draw in the order from the back to the front. You can use Painter's algorithm to do that. I believe so. But either way, it's one of the standard drawing algorithms. There's several of these kind of algorithms out there, but the point is that you could use a priority queue, for example, to accomplish this. And also one other detail is that you can also use priority queues for a couple other applications, which I'm hoping to show you in the next couple lectures. But yeah, they are an interesting blessing of a data structure. And if you want to just turn it into a queue, notice that all I have to do is just make sure I just make them so they all have at least. So keep in mind, if I want to make it like a queue, if I want to make sure I impose some sort of behavior on this thing, you could think back to the discussion I had earlier. You can always make it so it operates like a queue by either putting the priorities in an order so that you always make it so that the ones that come in the latest always have a higher number or higher key, meaning it's less important. Or if you're doing an underlying data structure where you know it's always going to break these ties by placing it at the end of a grouping, you can always just set them all to have the equal priorities. Sorry, I get very excited about this. But yeah, there's many applications for where you could use priority queues. I'm going to talk about some of those, and depending on how much time I have, I might even get you to take a peek at one. But I want to talk about a simple implementation for a priority queue. So you know how to implement a queue, right? There's several ways to implement a queue. For example, you could do it with an array. You could do it with a linked list, for example. There's so-called, for a queue, you may use a so-called circular linked list. If you use an array, a common way of doing it is so-called using a circular array queue. Now, because we have a priority involved here, it's not as simple as just placing at the front or the front or the rear of the queue anymore, right? You might have it where if you got to think about it more like this bucket as opposed to just that line over there. It's because, remember, as long as I make sure that whatever comes out when I do removeMin is the correct element, it doesn't really matter what order these are actually in. So just keep that in the back of your mind as we're doing this. So I'm going to first start off by imposing an intuition that's very natural for that one over there, the one with my line. So one way you can implement a priority queue is using a so-called doubly linked list. So I'm just going to give you, if you've never seen a doubly linked list before, I'm just going to draw you a fun picture. Because you may have seen one of these before. I just want to give you the intuition behind this. So you could have front and rear. Sometimes people will call that the head and the trailer for this specific implementation. And what happens is you have it where the front is pointing to the first node, but each node has actually a pointer that it goes back to the previous node. Like this. So it has a next attribute and a previous attribute. And yeah, so one thing also worth noting is that when you get to the front of this thing, you're basically just going back around to the front over and over again. Just keep that in mind. It just... I had to make sound effects to make this dramatic for you. But yeah, so just to remind you, so a doubly linked list, you'll have it where there's a previous attribute, so that points to the previous node. Has a next attribute, and then this would be your, in our case, this would be your element. Remember, this is where you're going to store your key and your value. So that your data attribute is going to consist of a pair of pieces of data. The key or priority and the value or data. But yeah, so first, has anybody never seen a doubly linked list before? This is just a picture just to give you an intuition for what I'm going to explain in a moment. So if you've seen a linked list before, all you have to think about this as is I want to make sure I have access to the front and I have access to the tail of the linked list. And I'm just adding in these references or pointers to the previous nodes. That's all I'm doing here. Now, you can always get away with implementing these things cunningly enough without a doubly linked list. I just know that this is one of the more standard ones people like to use. So anyways, there's two different ways I can go about this. Two very simple ways. These are rather effective if you're dealing with a smaller amount of data. So one way you can imagine this is that the linked list maintains elements that are sorted, meaning that the ones that are sitting at the front have the smallest value, aka the key is the smallest one, meaning it has highest priority. And as I move towards the right, the key's values only get larger. They don't get smaller. So that's what I would mean by a sorted doubly linked list. In contrast, an unsorted doubly linked list, I would just, whenever I need to do an insertion, I always just do it wherever is applicable. So for example, I could just easily just jam this sucker on, like, say, the back or the front. It doesn't make any difference. If you view it more like a bucket, you could just simply just put it wherever you like, as long as you know how to get the one with the minimum element. Sorry, the minimum key. So I want to walk you through just the general time complexities for doing these two first before I show you a much more effective way of doing this. Because these look something more like what you may have seen something like maybe in like 210 where you have like some arrays or a linked list and you do some manipulations that way. I'm going to show you how you can kind of take this and jam it up to another level. So for example, if I have my unsorted doubly linked list, if I want to just do an insertion, I could just put it wherever. I just create a new node. I can, for example, just stick it on the front or the rear. For custom purposes, you might just stick it at the rear of this linked list or the tail of the linked list. You may make a new node, place it over here. You may do that. That's one way you could do it. If you want to make it operate more like a queue, you might traditionally put it over here. So you could get away with doing this in constant time. However, the penalty is that if it's unsorted, you have to go through all the nodes. You have to traverse the linked list and find the one with the minimum key, right? So you have to traverse through the linked list in the worst case. So notice that requires you to take linear time in the worst case. So, for example, if I proceed this way, what I could do is I can look at removeMin. Same idea, except instead of looking for just the minimum, I would remove the node from the linked list. I would retrieve the element from it, and obviously I'll get rid of this node itself. I have all what I need, and I can just return that element. So I could do that in linear time by the same rationale. It's just that I need to actually remove the node from the linked list. And then lastly, these two you could just store as attributes, right? You could just keep a counter of how many elements you have. Both of these can be accomplished in constant time, regardless of the structure of the linked list, or a doubly linked list. Now, in contrast, if I maintain a sorted order for the elements where the keys are always going to be so that when I look at all my elements from left to right in my doubly linked list, the smallest one's always going to be at the front of the doubly linked list. So in this case, what that means is that whenever I want to do an insertion, there's a possibility that I might have to bring it all the way to the end, because it may have a very large value for the priority, right? It may in fact be the largest value. So that's why, for example, if you wanted to insert into a sorted doubly linked list, it may take linear time, but here's the trade-off. So notice that these are actually quite naturally trade-offs with each other. So now in contrast, because I know exactly where the minimal element will be, the one with the minimum key value, they're always going to be at the front, right? So I could get these right at constant time. It's just a constant number of pointer manipulations for my doubly linked list. So I could do all of these in constant time. This is no different, same rationale. But does everybody see the trade-off between these two implementations? Does everybody see that? So notice that in one case, I kind of make insertion really easy to do. But however, removing or retrieving the minimum key value element, that is tougher, right? In the worst case. In contrast, if I maintain that it's sorted, the insertions might be tough. However, the removals are very easy to do. So do you see how these both have a very natural trade-off between each other? So if you were to pick one or the other, it depends very closely on how you want to use these implementations. But these are effective and simple to implement, and they're very effective for smaller sets of data. So if you find yourself just really needing one, you can always whip together a doubly linked list, and you could carry out this process. But are there any questions about this? So this is just a simple approach for implementing a priority queue. There's several different ways you can do it. This isn't the only way to do it. This is just one example. But notice that this is not too bad, right? Especially if you know more about your data. So this is effective. Effective for smaller inputs, right? Now, when I use the word smaller, I'm still talking like magnitudes of hundreds, right? That's pretty good, right? But if I wanted to do this with, say, a priority queue that has millions of elements, if I were to run into that linear case many times, I don't know, maybe it might make a little bit more of a dent in terms of time complexity, right? So would it make sense to use a list of lists for each k? Now, keep in mind that if we have our keys, so if you know each one of the priorities, you could indeed bucket them. For example, you could have the idea that you have a list for the ones of priority of a certain value, then you could have one for a next one, and so on and so on. Is that what you're suggesting? Is that I have, like, say, for example, a bucket. So, for example, all the ones with, say, for example, the keys or the priority is 0. I put all of those in a list that goes in this bucket. And then all the ones with priority 1 into that bucket, 2, and so on, and 3. And say, I don't know, there's some upper bound on this. Maybe I'll call it capital C. Yeah, no, wonderful. So that's a very interesting suggestion. Now, I like that suggestion, but I will tell you one thing that might be a bit of an issue for us. It depends highly on the value of, like, the maximum value a priority can have. So in this case, actually, I really like your suggestion, because if I know that the values that the priorities can take on, you can almost think of it like a numeric range. For example, if I know, like, say, for example, all the priorities, these k values, they're in an interval that goes between, like, say, 1 through, I don't know, we'll call it capital C. If you know that, if it's between 1 and, say, C, and you know C is not very big, that strategy might be quite effective, but I must stress that now you've thrown a dependency in the running time of this thing. Because every time you have to, say, remove min, you have to keep in mind that now you have to examine this, potentially you may have to scan through all these lists, right? But now, notice the number of lists now depends on this capital C. But this is actually not, it's now you've introduced what we call a parameter to the problem, which if this is just a constant, that's great. If it's a small number, in practice, it's wonderful. But notice that now I've introduced something where it's almost going to be kind of like if you think back to hashing, for example. If you have to think about, like, I'm almost like examining through these until I get one that I can remove out of it. So in some sense, it's almost like I'm suppressing this worst case, just it's in lists of lists, but now the number of these can actually now relate to this other parameter now C that's independent of n. So keep in mind that now it makes things a little bit more interesting. I really like that suggestion though. If you know, for example, that the number of buckets that you have is a very small number, like 3, for example, this may be an effective strategy. So I really like that suggestion. But yeah, a wonderful one. I really like that idea. I like it when students can think about these things, because that is actually another thing to keep in mind is that, okay, so what if the priorities are only of a closed range? Like say they're only between some value and this other value. This is something to always take in consideration when you're studying a problem, because it often will you get behavior and certain structure for your problem that you wouldn't otherwise get more generally. So when we're looking at this problem, notice like our ADT, I don't make any assumption like this. So now when it becomes a problem like this, now you'll notice that all I'm doing is adding more things on top of it that will, at the end of the day, still kind of suppress the worst cases that I have up here. But now you have this extra variable that you have to be considerate of. Yeah, no, I really like that suggestion. But anyways, what I want to do now is I want to show you a very effective way of reducing this issue. So notice that there's this giant gap between the constant and the linear. It'd be very nice if I could bring down that linear term to something a little bit more manageable when we deal with very large sets of elements, like a very large collection of them. So I'm going to show you one very important tool that it's part of the mayonnaise crew, the M-word crew. They are going to be something that are going to be very helpful for us for modeling out a priority queue. And I assure you that once you finish learning a bit more about this, you'll see and appreciate hopefully this bucketing, this idea of thinking about the priority queue as a bucket instead of thinking of it more like a line once you see this idea. At least I hope so. But keep in mind, I'm happy to see any kind of ideas that you may have. So what we're going to talk about are heaps. So we're going to talk about heaps. So this is going to be a very interesting tool we're going to use. Now the great thing is that you know most of the things we need to talk about him. Is it going to be something too alien? So here we go. So we're going to be considering, we consider binary trees. So we're going to consider binary trees. So the first thing is we're going to consider binary trees. Now, do I need to remind anybody about what the definition of a binary tree is? It's okay. I'm happy to do so. Yeah, just let me know. I can always write down the definition. Sure, I will give the definition of a binary tree. So let's talk about what a binary tree is. So binary tree, it's what we call an ordered tree. An ordered tree where every node has at most I lost my penguin friend. At most, 2 children. At most, 2 children. Where each child node is labeled as either a left child or right child, or a right child, a left child precedes a right child. So just remember, we're talking about a tree where there's an ordering imposed on the children of the nodes. So there's a left child and a right child, and we always assume that the left child comes before the right child in this ordered tree. So is this clicking with everybody? You may recall this. This is something that you may have learned when you talked about binary search trees, for example. But this is more broader. It isn't just a binary search tree. It is just a binary tree. So I'm not imposing any additional structure other than the fact that there's a left child and a right child. So now I'm going to define what a binary heap is. A binary, my Y is sort of melting into the R. A binary heap is a binary tree that satisfies two properties. So there's going to be 2 properties that a binary heap has to satisfy. So the first one is what we call the heap order property. So I must stress that you're going to find that when we work with this data structure, that the idea is that we're going to make sure we maintain a binary tree that's going to have these 2 properties that I'm going to list whenever I do an operation. So prior to the operation, it has to satisfy these 2 properties I'm going to list. And when I ever do an operation, I'm going to have to ensure it stays that way afterwards, that it satisfies these 2 properties. So just keep that in the back of your mind when we're talking about this. So the heap order property is really quite simple. For each node, which sometimes I'm going to refer to as a position, because one of the more popular ways of implementing a heap uses an array, and it's a little bit easier to talk about the nodes as positions in an array, for example. For each node or position, P, other than the root, the key of P is greater than or equal to the key of its parent. So that's the first one, is that if I give you any one node other than the root, if I look at it and I examine its key, so if I examine the key that's stored with that node or position for that element, it has to be that it is greater than or equal to the key of its parent. So I'm going to show you an example in a moment for what I mean by this. So that's the first property. The other one is what we call the complete binary tree property. So this maintains a certain shape for our binary heap. So complete binary tree property. So this is the other property, is the so-called complete binary tree property. So here's how it goes. So a binary tree of height h of height h where levels I is equal to 0, 1, all the way up to h minus 1. So remember, there's two concepts with the tree, right? We have the height of the tree and we have the levels of a tree. So remember, we start at the top of by the root. You start with there being level 0, then you have level 1, level 2, level 3, all the way down to level h minus 1, except for we're not going to count quite yet the last one. So keep in mind that I'm just iterating over these specific levels. Each of these have 2 to the power of I nodes. So you may actually recall the other lecture, we actually used this property, right? We took advantage of this idea when we were talking about the maximum number of nodes that can occur at a given level. This is equivalent to me asking you about if I had a binary tree at a given level where all of its leaves are on that level, and asking what's the most number of nodes that could be at one level, or the maximum number of leaves that could be at a level. You could actually equate it to something quite similar to what we talked about the other day when we were talking about comparison-based sorting. This is where that 2 to the I, by the way, comes from. So it's not anything out of the blue, it's just a property of a binary tree. So we're going to ensure that I have this. So I want to make the tree as full as possible. I want to make sure that there's as many, so if I have any one level, I want to ensure that there's so many that all of these levels from 0 all the way up to h minus 1 are all full of nodes. I want to make sure of that. This is the maximum possible at each of those levels. The remaining nodes at level h, so this is the final level, the bottommost level, at level h are in the leftmost possible positions. So the way you got to visualize this thing is that you're going to have it where you have this first property that maintains the ordering of keys in the tree. But notice it's not as necessarily as strict as like the binary search tree property. Say for the binary search tree. This is a little bit looser. Likewise, this actually enforces a shape to the tree that all the levels except for the last one may not be, so all of those before the very bottom one are going to be full of nodes, except for the bottommost one. Now what's going to make this a little bit different is that all of the nodes that are on the bottommost level are all shoved to the left as much as I can. So you might sound a little bit weird when I think about that, but remember it's an ordered tree, so I could talk about nodes being as left as possible. So I want to show you an example of what I mean by these two properties so that you can see what I mean by this. So before I proceed, can I move over to the other board, or is anybody still copying down? I just want to make sure. Because I want to draw you a fun picture. Just to give you an example, just to reinforce these two ideas. Okay, so let's boogie on over this way. So I'm just going to kind of boogie on over this way. Let's go this way. As I put the eraser over here, let me walk over here. So let's go over here. So let's... So I'm going to draw you a picture of one of these so-called binary heaps. And you're going to see that there's something really interesting about why we're going to call this a heap. So I'm going to draw an example of one such heap. So the root of this is going to be 5. The left child is going to be 6. The right child is going to be 8. The left child of 6 is going to be 7. The right child of 6 is going to be 10. The left child of 8 is going to be 12. The right child of 8 is 11. And the left child of 7 is going to be 14. The right child of 7 is 22. The left child of 10 is 18. Squeezing it in there. The right child of 10 is 17. The left child of 12 is 15. The right child of 12 is 13. And that's the entire tree. So if I'm reading this off from level order, it's 5, 6, 8, 7, 10, 12, 11, 14, 22, 18, 17, 15, 13. So this is an example of one of these binary heaps. So, I have a very interesting question for you. Now, suppose that I had one of these so-called binary heaps. I have a question for you. Before that, let me just reinforce just those two definitions, just to make sure we can confirm that this is in fact a binary heap. Notice that how many levels do we got? We got 0, 1, 2, 3. And notice that 0, 1, and 2, notice that all of these are completely filled with nodes. There's no space for me to jam another node in, right? However, the bottommost level, notice that all of them are to the left as much as possible. There won't be a node just sitting, like there won't be like one right here. That would forbid, that actually will violate the complete binary tree property. So we're allowed to have this bottommost level have a little bit of freedom, but all of the nodes in the bottommost level have to be to the far left as possible. So this is just, so one thing I actually want to bring up is this a binary search tree? Just a question. Is this a binary search tree? No, right? It's not a binary search tree. Can somebody tell me why? Yeah, exactly. So notice that this is not a binary search tree. Notice that it's not maintaining the so-called binary search tree ordering or property. So the binary search tree property imposes that if I look at any one node, all the keys to the left of its left subtree, all of its keys have to be of smaller value than itself, and all the ones in the right subtree I'll have to have keys that are larger than my key. That's what the binary search tree property is. Now, this is a little bit, look at this, a little bit more loose. That's one way I could say it. In terms of the key values, it's a lot more loose, which at first might look a little jarring for somebody. But notice that it does, in fact, it does satisfy the heap order property, because if I look at any one node, notice that its value is greater than or equal to its parents. So notice that 6 is bigger than 5, 8 is bigger than 5, 11 is bigger than 8, and so on. So we know that this is a binary heap. Now, I have a question for you. Now, this is the thing I really wanted to get to, but I wanted to reinforce that definition, is where, if I were to imagine this, just imagine I had this structure, and imagine that these numbers were the keys of elements for my priority queue. So if I wanted to do removeMin, where is that element in my tree? Where is it? Is it down here? Where is it? Like, guide me, where is it? Which one am I supposed to, yeah, the root. It's up here, right? It's right up here. It's right here at the root. So, the root contains a key of min value. Now, one thing I didn't tell you quite yet is that what I've defined for you is something called a minimum heap. So what we've just described with our definition is a minimum heap, or the shorter term is just min heap. Now, if you want to talk about a max heap is just simply where you just take the heap ordering property, or the heap order property, and you just flip the relationship. So for example, if you had a max heap, what would be sitting in the root is actually the element with the largest key. And you would impose that if I look at any one of the nodes, if I look at its parent, it has to be at least me, right? It can't be, sorry, it has to be that this is, sorry, I had it back. I'm getting a little ahead of myself, as you can see. If I examine this node, whatever's sitting here most certainly has to be either smaller than my parent or equal to it, right? So that's what a max heap is. So that's the only difference between these two things. So a min heap is just where you're going to maintain that the heap order property has this relationship. A max heap is just where I flip that relationship. That's it. Nice and simple. Now, here's a neat property that binary heaps have. So this is kind of like, if I could call it like a killer app, I don't like using that phrase, but it most certainly is for the binary heap. So I'm going to give you the theorem. I'm going to leave the proof for you to read if you want to take a look at it, if you'd like. I won't test you on it. I just want you to be aware of this property. So this is like the killer app of binary heaps. So the height h of a heap. So whenever I talk about binary heaps at this point, I'll just refer to them as heaps just for brevity. A heap T with n elements is h equal to the floor of log base 2 of n. So just to reiterate, if the height h of a heap T with n elements is h is equal to the floor of log base 2 of n. So remember, it just means I'm rounding down log base 2 of n. Now, I want you to think back to thinking about binary search trees. One thing that you might have thought about when you thought about binary search trees is the fact that often the operations involve the height of the tree. It's going to be no different here. So in this case, notice that what I'm telling you is even with these very lax conditions, they seem rather lax, except for maybe that one involving the shape of the tree. With this really lax condition, as long as you have those two properties at play, you can guarantee that the height of this binary heap is always logarithmic. So if, say, for example, I have an operation that depends on the height of my tree, I'm telling you that if it's, say, for example, big theta h, where h is the height, you could simply replace h with log n. So you get logarithmic times if you could take advantage of the structure of this tree. So that's what I'm going to be trying to do, is I'm going to be trying to show you how you can implement one of these using a very simple data structure. But also keep in mind that this is still a literal tree data structure you could implement. So you can implement this as you see it, like where it has a left child, right child. These are things to keep in mind when we think about this. So are there any questions about this property just before I proceed? So that's kind of the game plan, is I'm going to try to take advantage of the structure of this binary heap by trying to find a meaningful way of doing each of the operations with my priority queue. And if I can maintain those two properties for my binary heap, the so-called invariant that I want is I want to make sure property 1 and property 2 stay true, regardless if I do one operation or two operations or three operations, they mutate the tree. This is no different, by the way, than, say, when you did this with a binary search tree, or if you've seen an AVL tree, for example. Same idea. But it's just different structure and different properties we're using. So the big thing I want you to think about is that as long as we can maintain that this is a binary heap, that the height is always going to stay big O of log n. That's all you have to remember when you think about this. So if ever we have an algorithm that depends on the height of this tree, if I can ensure it's a binary heap when I'm done, if the running time depends on h, the height, then it's logarithmic. That's it. Isn't that neat? So we're going to use this to develop an implementation for representing this tree. And it's really simple. It's like one of these really nice classic ways of approaching this. So I want to show you that now. Actually, I think I'm going to stop right there. So let me just let me just make myself a little mark here so I'm not too far to the left. Okay. I'm giving myself guards, okay? It's like training wheels. It's like training wheels. Training wheels for lectures. So let's see here. So, why? Because I want to use this picture to help us. So we're going to talk about an array-based implementation. So I must stress that if ever you wanted to, you could actually implement this tree that I have here. In the most literal sense, just like the same setup you would have for a binary search tree, just the algorithms would be different. So you could take all the operations I'm going to show you, you can actually augment all of those to operate and directly manipulate one of these trees if you wanted to in a linked-based way. Just like what you see when you manipulate a binary search tree. So the first thing I'm going to remark is that for many problems, we know the size of the heap. So I'm going to just assume that this is the case. So I'm going to assume that I know how big the heap needs to be. So what I'm going to do is I'm just going to make this assumption, and I'm going to I'm just going to assume that when I have my array, I always can make it big enough to store all the data I need. That's the thing I'm really saying here. Now, if you did not have that, you would have to follow you may have to pull out what we just talked about the other day for resizing the array. And you could use that practice here too. So, like I said, a lot of these ideas sort of generalize nicely. So I'm going to just say represent a binary tree. Represent a binary tree of n elements. That's an S there. N elements using an array. Of length at least n. So I just want to make sure it's big enough. Like I said, if you have it where you're going to need more space, you would use the resizing scheme I talked about the other day. For example, you could use that. And it does guarantee those amortized bounds I talked about the other day. You can actually generalize that analysis for this situation too, which is really interesting. But anyways, so I'm going to say we can compute a position of P, where P is a node that's going to be in my tree over here. A position of P using a function f as follows. So I'm going to give you some rules for how we compute parts of the tree. So all of these nodes are going to correspond to positions in an array. So at first it's going to look a little abstract, I admit, but once you see it in the picture, it's going to be very simple to play around with, just to be very clear. So at first you look at it like, I don't know, I don't really get it. You'll see the picture over there and be like, boom, okay, that seems really simple. So you're going to imagine the P is like a node in this. So if P is the root, then f of P is equal to 0. So the root is always going to be in the 0th position of the array. It's always going to be the first position. If P is the left child of some position, of some position Q, then f of p is equal to 2f of q plus 1. You're going to see what I mean by these in a moment. So if you're looking at this, you're like, okay, well, what is f of q? What is that? Remember, this is a position in the array. So wherever the position of the parent is, you're going to multiply that by 2, and you would add 1 to it to get the left child. Now, if you want to get the right child, so just to abbreviate this to make this a little bit easier for me to write down, if P is the right child, so of some position Q, so if I have the right child, it's just simply that f of P is equal to 2 times f of Q plus 2. So instead of adding 1, you add 2. So I have these pieces of information that can help me. So why don't we see what this actually represents for a heap like this one. So let's see what that does. So let me draw out an array. I'm going to call this array A just to keep this simple. Is it okay if I erase the theorem here? Okay, I'm going to get rid of this theorem here because I want to write down the positions. Now, I don't know how much more space we're going to need to write all these positions down, but we're going to make it work. So, because we have, I think we have like 13 elements here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I needed a little bit more space there. I need to move over the board. Let me move this over a little bit. The other way around, camera. There we go. Wonderful, wonderful. The camera wanted to go that way. Okay, so anyways, I'm going to now try to fill in this array based on the function I've just described here. So remember, it says that the root is always in the first position. So it's in position 0. So 5 will go right here. And now, if I wanted to figure out where this node and this node, what would they be in the array? Well, look at its parent. Its parent is in position 0. So it's 2 times 0 plus 1, which is just 1 for 6. And for the right child, is 2 times the position of the parent plus 2. 8. And while I'm doing this, I want you to notice the order in which you can read the elements from left to right as I'm doing this. So I'm going to fill in the rest of these. So I'm going to have 5, 6, 8, 7, 10, 12, 11, 14, 22, 18, 17, 15, and 13. So there's my array, and it has all my elements in it. Well, these are the keys for those elements. Now, does anybody see anything that's very easy to look at with my array here, based on the structure of the tree? So first, all I did was I applied this. If I were to just carry this out, I could just simply get which each one of these are. So if ever I'm at a given position, so for example, suppose I'm in position 2 here, and I wanted to figure out what the left child of 8 is, all I have to do is multiply its position by 2, right? And then I add 1 for the left child and 2 for the right child. So if I take 2 times 2, that's 4. And then I add 1, and that brings me right here. See, notice it's right there. Likewise, its right child's right here. But there's a very interesting thing that's going on with this function. Does anybody, if you think about this from a tree traversal standpoint, say for example, there's a very specific ordering that all of these nodes are, all these elements are in the array. Did you notice I read this out to you initially when I first wrote these down? Remember I described this in a very specific way to you. Do you remember what I did? I talked about the levels of the tree, right? So here's what I want you to do. Start up here and read from left to right as I go down the tree. Notice it's left to right in the array here. This is a level order traversal of the tree. So notice that this is actually a very easy, so if you ever find yourself just unsure what to write here, if you're looking at what your tree should look like versus what the array is, just simply follow through the tree in a level order manner. Start from the left, go to the right, level by level. It's just a level order traversal of the tree. It's very easy to read off once you notice it. Is that kind of cool? That's really a neat structure of this thing. So, natural question is what we're going to do now with this thing to make it so it does all the operations for our priority queue. So now, one question actually I do have, but I think for the purposes of time, I'll just answer it for us. So remember, the root is always going to have have an element with the minimum key in it, or minimal key. We're using plurals here. So if ever I want to get the parent, by the way, one thing I didn't mention to you quite yet, this is sort of, I wanted to talk about it, but I'm looking at the time and I want to just make sure we could get to at least one of the algorithms today. So if P is not the root, then the parent of P is located at the following position. Let me move over the camera, because I know I'm writing a little to the right. Let's move me back over here. So I want to tell you where the parent can always be located, because this is an important detail for a little later on, and we'll talk about it next time, but let me just talk briefly about it. So if you ever find yourself wanting to know where the position of the parent is, so if I look at any one of the nodes here, or positions, if I wanted to know what the parent is, so for example, for 22, I should get 7. So if I want it would be in position 3. The parent here would actually be computed by going f of p minus 1 over 2, and you round that down. So if I give you, for example, say for example, I'm looking at 12 here. The parent of 12 is 8, right? Because I just simply take 5 minus 1, that gives me 4, and then I divide that by 2. So 4 divided by 2 is just 2, and it's right there. So keep in mind, this is a very nice and easy data structure you can play around with, right? It's just an array, and we know exactly where everything is in the tree, and it's very natural to read off. Now I must stress, you might ask, Dan, why do I care about those two properties for our binary heap? Why should I care about the ordering? So the ordering is very helpful for us when we actually look at how we computed and figured out where all the positions are. That's why the heap order property is very important. The so-called complete binary tree property, this is important because if you look at my binary heap here, look at how it corresponds to my array here. Because all the elements in the bottommost level are all shuffled to the left as much as possible, notice that there won't be any so-called gaps in the array. If, for example, this 13, for example, was, say, over here, the right child of 11, you would actually have 2 blank spots, and then 13. So you can use this implementation, for example, for any binary tree. It's just that you don't want to have these gaps. And 2, the heap ordering property, we're going to use that for our algorithms. You're going to see that they're going to be rather straightforward, which is wonderful. That's what makes this implementation very nice. So, anyways, with the time we got, I want to show you how we do an insertion through the insert operation. Are we okay with doing that? And then we're going to wrap things up from there. So, let's do the insertion, okay? Let's head on over here. Come on, camera. Come on, I'm over here. Come on. Here, let's go this way. So let's go this way. Let's talk about insert. Now, when I talk about these algorithms, I'm gonna just let you look at the pseudocode in the notes, because once you get the idea, you don't, the algorithm itself is just once you understand the idea that pseudocode is very natural to read off. There might be another ulterior motive why I also want you to look at the notes when you look at the pseudocode as well, but I'm not going to talk about that. So let's talk about insert. So, insert. Ah, here we go. So let's talk about insert. So remember, insert takes in a key and a value. So all we're going to do is we're going to store this pair as a new node. So we're going to make a new node for this in the heap. Now you're going to notice the way I'm going to phrase this is as if it was a tree. So just be aware that I'm trying to describe it like it's a tree, but it's very natural to talk about it as the array. That's why you'll notice I'm using position and node. I'm using these terms like synonyms. This is very deliberate. So I'm going to, as a new node, and then what I'm going to do is I'm going to increase n to be n plus 1. So I'm going to increase the number of nodes by 1. It will be placed on the deepest level, but furthest to the left possible. Because remember, I need to maintain that complete binary tree property, right? I need to make sure that when I bring something in, it's not like hanging out all the way over here. I want to hang out with all my friends over here on the furthest left in the bottom level. So we need to maintain the heap order property. So we will bubble up. So we will bubble up. Some people call this percolate up. I call it bubble up. I think it's a lot more fun. Bubble up the new element until satisfied. So what I'm going to do is I'm just going to quickly draw this heap over here. Actually, I can use the one I have over here. Let's use that one. So let's boogie on back over this way. And I'm just going to try to do an example with you for what I mean by this bubbling process. So you might ask, Dan, what does it mean to bubble up? Now, one thing that you'll know about bubbles is bubbles tend to float, right? So imagine you have a bathtub and say some bubbles form. And what I would like to happen is that I want to imagine that these bubbles will float up to wherever there should be appropriate based on the density of the liquid. So in our case, water, we want to get it to go up as high as it can to the surface, right? So the idea is that I'm going to try to find, so I'm going to just jam the node in, right where I need it to be for the complete binary tree property of the hold, and then I'm going to allow it to make its way up the tree through swappings of nodes. So here we go. So what I'm going to do is I'm going to try to now insert, let me just get my eraser. Let's get my eraser. Let's knock this sucker out. Let's do this. Okay, so what I'm going to do is I'm going to insert now a new node. So I'm going to do insert. So I'm going to do insert, and I'm going to give it, so the key is 3. I don't know what its value is, but I'm just going to have it where its key is 3. So when I do this, I'm just going to put 3 right here. in this new position. Remember, I'm just going to assume that the array is long enough so that I could do this. So now the left child of 11 is 3. So I just put it in the deepest most level furthest to the left. That's the first step. The second step is now to do this bubbling up or bubble up procedure. So now I have a question for you. Is this 3 in a spot that satisfies both properties of the binary heap? So first, I recommend looking at what this value is and compare it against its parent. Now, right, it violates the heap order property. So here's a very interesting idea that I'm going to propose for you. Now, because of the definition of the heap order property, we know that its parent has to be, so if I want to maintain this property, right, notice that when I look at 11, for example, its value is greater than or equal to its parents, right? So what I want to do is I want to make sure that's maintained. But here's the neat thing. All parts of this tree maintain that property already. So all I have to do is I'm going to do something kind of neat here. So watch this, watch this. So what I'm going to do is I'm going to swap. So I'm going to swap the elements that are in these two nodes here. So I'm going to swap 11 and 3. So I would swap 11 and 3. So I swap these two. Now, I have the same question for you. Is this a binary tree yet? Sorry, a binary heap. A binary heap. Are we done yet? Not yet. No, not yet. Notice that I could do the same exact thing, but notice that every time I do this, if I look only at this heap right here, suppose that if I rooted a tree at this node, notice that everything below it maintains the properties of a heap. This is one thing I want you to keep in the back of your mind when we talk about this next class. So notice that now all I'm going to do is I'm going to now swap the elements that have 8 and 3. I'm going to just swap these two. I'm going to bubble it up. 8, 3. So where's my 3? I have 3 here. 8, 3. And now, am I done yet? No, right? I'm not done quite yet. I need to do one more swap. I need to swap 5 and 3. So I do another swap. I swap 5 and 3. Now am I done? Am I done? Is this now? Are we okay now? Yes, we are. So this is actually all the bubbling, this bubble up is. That's all bubble up is you go through. So all you do is you compare wherever you just inserted in the position here. You compare it against its parent. If its parent ends up being bigger than yours, you need to swap them, right? So if it's violating the heap order property, you swap them. You keep doing this process. You just keep following along up the tree, which we can always access its parents. We have a formula for that. So what we just do is repeatedly do this over and over again until we maintain the heap order property. And because every other part of the tree maintains this heap order property, we know that we're not mutating any other part of the tree except for all the stuff that is directly of its children. In particular, the children for which you took the path upwards. Now, question for you. So this is the last thing I have to say, and I'll let you go. Notice, so I have a question for you. What's the worst case time complexity of this? So notice all I did was I inserted an element into this position, which I could do because the array has space for it. I know where exactly this is. So this takes constant time. But notice, how many swaps do I have to do? It's logarithmic. Perfect. So the worst case time complexity in this case, it's just simply big theta of log n time. So if you want a more careful explanation of this, it's just sitting in the notes. That's all I have to say today. So when we come back on Tuesday, we'll finish talking about heaps, okay? Yeah, so keep in mind that we're going to take advantage of this swapping or this bubbling process for all of our operations. So there's a different way I have to do it when I have to bubble down. That's what's going to be a little different when I look at the removals. So next time we'll look at that, and I should be able to cover the rest of everything you need for assignment 2 then, okay? So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.